Hi everyone, and thank you for joining this session about automated performance optimization. Akamas is a newborn company within a bigger group called Moviri. Within Moviri, we have been dealing with the performance engineering and optimization activities since the last 20 years. In all this time, and especially in the last years, we have seen quite a lot of changes in the applications and in the environment of our customers. First of all, the technology has changed. JVM and databases, for example, have evolved. And as they get more mature, counterintuitively they also get harder to optimize. Each JVM release brings a new breed of features for developers or operators, along with a new set of parameters that can be used to tune them. And we have just passed the barrier of 800 parameters on that single layer of the whole IT stack. Moreover, also the number of layers in the stack have exploded. Some years ago, we were running applications written in C, compiled for a specific architecture on bare metal servers. Now we run applications written with some frameworks in high-level languages, executed by a JVM within a container, hosted on OS within a virtual machine, managed by some hypervisors. All these layers have their own parameters and complex interaction within each other. Think about the problem of sizing the heap of a JVM and the memory limit of a Docker container. The two parameters have to be set accordingly for the whole application to play well. Nowadays, customers are also building a wide range of applications, each one different from the others. Also, the way users interact with the application might change within the day. Think of an internal website of a bank where all employees do a lot of logins early in the morning to interact with other APIs for the rest of the day. The behavior of the application might change dramatically due to the change in the user behavior. Even when optimizing a single parameter for a single layer, we often encounter counterintuitive nonlinear behaviors. In this example, both increasing or decreasing the amount of memory used for caching in a particular database improves the throughput. Understanding this behavior requires many tests by changing just a single parameter. Finally, with the advent of agile practices, dev teams are increasing the release frequency. As traditionally, performance testing and optimization activities are executed before deploying a release to production, this trend leads to a reduction in the time available to run these activities. Still, the potential benefits of properly configuring your production environment is very high. This example shows the results of a paper we published at CMG 2015. Where we reported the outcomes of a manual optimization activity we performed from one of our customers in the insurance sector. The three curves represent the workload and the CPU utilization of the application we were optimizing for 3 working days. By changing just a few parameters related to garbage collection, we were able to reduce CPU utilization of the production cluster by 75%, supporting about the same workload. The costs of not doing this activity or doing it only when an incident occurs are evident. Overutilization and overspending, poor customer experience, which is known to have a close link to conversion rates. Releases get delayed due to performance issues, and a huge manual effort to identify and solve these problems when they arise. Given the growing complexity we have just seen, the required level of expertise, and the variety of technologies we have to interact with, we argue that manual performance optimization is not anymore sufficient to run this system at their best. Lucky enough, some approaches to cope with complexity in IT systems has also been developed. Among all, 2 are the main tools that we can leverage to ease performance optimization activities: automation and the AI. Automation has come into play first in the operations field, in order to reduce the manual effort of running some tedious and repetitive tasks, as well as increase the confidence in building a well-defined environment. Developers have also embraced it through continuous deployment in testing and performance environments. This led to best practices like versioning application configuration along with the application source code. Activities like restoring database state before running a performance test can now be run with the same tools developers use to provision their own testing environments. Also, the practice of testing from a developer perspective is evolving. With the shared responsibility of production environment, Developers are more inclined to extend their traditional automated unit and integration tests to functional, end-to-end, and even performance tests. Almost all of the most popular CI tools provide some kind of performance plugin to include the results of performance tests in CI pipeline. Even though the main goal of these kind of activities is avoiding performance regression, we can improve these pipelines and start some optimization activities also in this stage. We have seen that automation can free performance engineers from tedious time-consuming tasks, freeing up their time for more important activities, like analyzing test results and defining the best configuration. Still, the complexity of the environment has to be addressed. To cope with this problem, at Akamas we've built a proprietary machine learning algorithm to find best configuration. As we said, the environment we want to optimize is quite complex. From an optimization point of view, there are many challenges. The cost of running a performance test to evaluate a configuration is quite high in terms of time and resources. IT environments can be quite noisy. The possible configuration space is huge and complex, and it's almost impossible to precisely model the whole environment. Finally, each customer might have their own specific goals and requirements. Some might want to optimize for efficiency, others for user experience, others for supported throughput. From an optimization point of view, the ideal optimizer should address these challenges by supporting the specification of custom optimization goals and constraints, requiring minimum modeling input or none at all, should be robust to noise, and being able to converge fast to optimal solution, without being stuck into local minima. We can broadly divide the state-of-the-art approaches into three categories. Model-based approaches use established performance models like queuing networks to evaluate the performance of a system. These analytical approaches are fast and could be applied even before building the real system. The main problem is that modeling the entire system is very hard, and most of the performance models rely on assumptions that are not always fulfilled in the real environment. As an analogy, it's like designing a new airplane using fluid dynamics equations to find out if it will be able to fly. Other approaches build a simulation of the real system by gathering some data, and then optimize the simulated system. The main drawback of these models is that they require a good amount of data in order to model the real system, and their accuracy is very limited when unknown configurations are evaluated. It's much like building a small-scale airplane and testing it in a wind tunnel. It's much more realistic than the analytical model, but still does not provide enough confidence. Finally, test-based approaches use the real system to evaluate configurations. These approaches are more accurate as the performance is directly measured on the system, but are much more expensive, as even a small configuration change requires the whole evaluation of the system. It's like building and flying a new airplane every time we want to test a small design change. At Akamas, we've chosen to use this last category. In particular, we have built a proprietary reinforcement learning algorithm that aims at minimizing the number of tests required to find the optimal configuration. Let's now take a look at some of the results that this approach can achieve. The following use cases come from one of our first customers in the financial domain. They asked us to maximize the number of payment transactions per second that a single node of their infrastructure was able to sustain without violating SLAs on the latency of payments. For this particular use case, we integrated Akamas with their CI based on GitLab. Akamas generated a configuration file for the application and pushed it to a common repository. The CI was then in charge of deploying the configuration to the application and restarting the environment. Akamas then integrated with load testing tools to drive the workload, gather metrics, and evaluate the configuration performance. This is a common graph used to summarize the optimization activity. It starts off with an evaluation of the baseline configuration, which in this case had already been tuned by experts from Red Hat and IBM in previous months. Then we have the first phase of the exploration, where the machine learning algorithm is broadly exploring the configuration space in order to get an understanding of the effects of all the parameters. In this phase, we are already seeing some improvements, but also some bad configurations being evaluated. In the second phase, the algorithm starts to show better convergence towards good configurations. Almost no configuration worse than the baseline are evaluated, and we see a consistent improvement. Finally, the algorithm further explores an area of the optimization space where the best configurations reside, improving them further. The final configuration increased the throughput of the application by 55% over the already manually optimized baseline. The overall optimization activity lasted less than 24 hours, with a total execution of about 30 experiments. Let's go deeper in the results analysis with another customer use case. This customer asked us to optimize the performance of a core application which allow users to look for a flights combination across several carriers. Their application is deployed in a Kubernetes environment and benefits from horizontal scalability. So they asked us to focus on maximizing the efficiency of a single pod by tuning the JVM running inside the container and right-sizing it. They also provided some constraints on the stability of the throughput, the error rates, and response times. Also in this case, they have already done some manual optimizations of the JVM, and they were interested in evaluating if they had already found the best GC algorithm configuration to maximize the throughput of their application. We then set up an optimization to explore the configuration space of G1 and parallel GC algorithms, and provided the following results. The baseline configuration was using G1 GC and had been already optimized. Akamas was capable of extracting only 5% more throughput. The best configuration found was using parallel GC, which they have discarded in the manual optimization activity. When properly configured, this GC algorithm was able to provide 23% more throughput than a baseline configuration. Let's take a closer look to some of the most important KPIs. Here you see a comparison of the throughput over time for the baseline configuration in orange and the best configuration in light green. On the right axis, you can see the number of virtual users used for the test. As you can see, the baseline reached a maximum throughput of about 11 transactions before degrading due to the higher workload. The best configuration had a similar behavior, but was also able to sustain about 12.6 transactions per second. A similar behavior can be observed also on response time. As you can see, the two configurations have similar behaviors under light load, but as we approach the maximum supported number of users, the baseline configuration response time increases up to 7.5 seconds, while the optimized tops at 5.5. Looking at lower level metrics, like the duration of GC poses, we see that at high load, the optimized configuration was capable of reducing GC poses from 200 milliseconds to just 40 milliseconds. It also shows an overall shorter poses for lower load levels. Finally, look from the container point of view. Throttling can be seen as a measure of the required CPU utilization of an application with respect to the one provided by the container side. As we see, at a high load, the container running the application with the optimized configuration shows a significant reduction in throttle time. This is an indicator of a better sizing of the container with respect to the application demands. The second optimization question we had was about improving the memory efficiency of the application in order to better exploit the horizontal scalability of their environment. We rerun the previous optimization by including the memory utilization as well as the application throughput in the goal, and expanding the optimized parameters to include also other JVM areas, like just-in-time compilation, GC parallelism, and hinder space sizing. We found out two very interesting configurations. The one that was providing more throughput, about 13.6 transactions per second, was using 35% less memory per transaction with respect to the baseline. The most memory efficient configuration was providing a little less throughput, but still more than the baseline, and was using about 76% less memory per transaction. We were now faced with an even harder challenge that came from the operations department. They asked Akamas to find a configuration that was able to avoid hard response time and throughput degradation, even when the workload was increasing. We added a minimum requirement on the supported throughput and increased the optimization scope to include also 3 parameters related to Tomcat. Similarly to previous results, we were able to improve the application throughput by 23% while reducing response time degradation at high load from 11 seconds up to 7.5, which was the highest value allowed by the constraint. Again, the two configurations had similar behavior up to the breaking point. Then, the original configuration degraded, reducing the supported throughput, and finally crashing, while the optimized configuration was able to keep serving a high number of requests, even if the traffic was still increasing. From the response time point of view, we see that the baseline configuration made the application run slower, as the traffic was increasing, leading to a crash, while the optimized configuration shows a smaller and stable increase in response time, even with a much higher traffic. Most of these benefits were obtained by right-sizing Tomcat queuing behavior with respect to the actual application capability. Again, another example of right-sizing across multiple layers. In conclusion, we have seen how the growing complexity of IT stacks makes performance optimization activities both more important and harder to carry out. Automation can help performance engineers spend their valuable time on core activities like result analysis or bottleneck detection. Finally, AI can help performance engineers to better explore the space of possible configuration and reach unprecedented level of performance. If you have any question, please join us in the Q&A session or later on in the panel discussion.
Awesome, thank you so much, Giovanni. It's another example of amazing usage of research to give us our free lunch for engineers. What could be better? So while we are waiting for questions to pop up, I again have a chance to just ask the question that I am interested in, and I mean there are lots of things to be interested here, but I'm curious about your I guess experience with building these sort of pipelines for production, and like how do you basically use them in production without having to use any testing, or like basically the idea is that how do you get this data in the least expensive way and also most representative way?
Okay, I hope you can hear me loud and clear. So yep. This is actually a quite common and hard question as well. So we currently have two different ways of doing this kind of optimization. The first one is running in pre-production and using a standard performance testing practices in order to have a significantly representative workload that we optimized against. With this respect, all the best practices of measuring your workload in production and then tuning your performance tests to have a significant workload is something that we always do. But then we are also moving to running these kind of activities in production. And clearly, optimizing in production has many different challenges. First of all, is how you guarantee safety into production environments. So in this case, we can leverage best practices of canary deployment and A/B testing, for example. So this is one point where we can integrate and then we try to look at the control group, which is the main pool of servers, and then run our configuration only in a subset of servers and to see if it changes. But one of the challenges there with respect to dev environments and pre-production environment is that we do not control the incoming workload. This is a very strong difference between a testing environment where we generate the workload and we know exactly what the workload is, and we can even change the workload with respect to what we are looking at. If we want to maximize the throughput, we can build a circular test. If you are running in production, we don't have the ability to do that. So what we are doing is we are expanding our algorithm in order to take into account also this kind of variability in the incoming workload in order to let Akamas and the overall optimization algorithm know what is changing in externally to the environment and treat it not as noise but as very important information. So this is one of the points. Another point that we've also put in our patent is allowing the algorithm to generate safer configurations. By using machine learning, we know how we think a certain configuration will perform before actually evaluating it. So we not only know what's the, let's say, the average value that we expect to find, but we also know some kind of confidence with how our configuration will perform. So we can use this information to make the algorithm generate configuration that are not only better with respect to a certain goal, but also safer to test in production. These are the main challenges that I see that we see in doing these activities directly in production, and we are challenging them from a research point of view, but also with some prototypes that we are running.
This is great. That's actually well. Ideally, I guess it would be great if we could use some sort of shadow traffic or fork traffic where we can just divert. Copy the traffic that goes into production and send it to a parallel instance with a different configuration in a safe manner. And I would imagine that that's actually one of the challenging things. I guess there are, with the microservices and sidecars, you can potentially try to isolate these instances to a point where you'd be able to operate in a more or less safe environment. But at the same time, it's probably also very challenging to make sure that you don't actually have any side effects, especially if you don't have control over the services that you operate on.
Definitely, shadow trafficking is also one of the other activities that we tested. We tested the tool called Go Replay, which was able to do either record and replay, so record production traffic and then replaying it into another environment, or shadow trafficking into a completely separate environment and then discarding the request that doesn't go back to the real users. That's also another good technique to link to the production, not directly canary or A/B testing, so where you're actually serving customers within your configuration, but still it's also, let's say, a middle ground between the dev environment, the performance environment, and the production one.
Awesome. Arun has a question. He says, great talk, totally agree. Can you share more details about AI/ML portion of the model? There is, I understand, a side that's involved in generating more data by running tests, but curious to know about how many runs to generate data, how to limit runs, etc.
Okay, so that's very interesting question. So I would say that I'll divide the question into parts. So the second one is related to how many runs it needs to converge and how long does it take to run. So that usually depends on many factors. The first one is let's say how long the test has to be in order to be representative. We've seen some approaches that requires many runs to converge. For example, genetic approaches are known to need a lot of configuration, a lot of individuals in the population to converge to meaningful solution. So they are very good in doing multi-objective optimization, but they require many iterations. And in this sense, if we are running performance tests that last maybe 1.5 or 2 hours, usually the time required to do this kind of activity is too much. So usually, as you saw in the example, we run about, let's say, from a few tens to maybe 100 or 200 of experiments in a certain study, so optimizing a certain configuration. And this is usually the amount of experiments that we have when we do this kind of projects. This is the reason why we choose reinforcement learning in general as a category in order to, let's say, explore the space and have overall better improvements even in the early stages. Again, another very important thing here is that we are not looking at the overall global optimum mathematically sure that there is nothing better. If we can get very close to that, still it's something that is a huge improvement with respect to the baseline, which is the default configuration or a manual optimized one. And as we get more and more improvements in the early stages of the optimization, this is even better. So when we evaluate our own optimizer, which is, let's say, starts from reinforcement learning and then include some of the advantages, some of our own modification to this kind of algorithms. We usually have a couple of metrics to understand if we do a good change in the optimization algorithm or not. One of these is actually measuring how fast we are in generating better, not the best, but just better solution at the very, very early stages of the optimization. Because if we can get, I would say, half of the overall improvements in less than 10 run, that's already a huge improvement in the real world. Because we can then start putting in production, then 50% improvement, and then going on to the other 50%.
Awesome, that makes sense. This is a very interesting topic, and since we have different optimization techniques involved, I actually hope we can continue the discussion during the panel. So I'm looking forward to hearing more thoughts on the best algorithms to use for these optimizations and also the future of this research. So thank you so much, Giovanni. We are unfortunately a little bit behind the schedule, so we're gonna take a quick 1-minute break, and we'll continue with Richard's talk in 1 minute. So come back in 1 minute and see you soon.